Good morning, everyone. So let me start MOSFET again because we could not do it yesterday. So let me start. MOSFET, metal oxide semiconductor field effect transistor. This difference I was telling in comparison with FET, MOSFET. Earlier we discussed FET, and I have shared FET PPT also yesterday. You can go through the channel, video channel, that is YouTube channel, and if you have any doubts, you can post me. Okay, I'll clarify. So MOS is an extra word, metal oxide semiconductor, that indicates it's the insulator that you are adding to the device. So insulator in the sense it is just a dielectric material, that is SiO2, silicon dioxide, that is placed this white color in the diagram. You can see this white slab, right? That is your SiO2, silicon dioxide, introduced between gate and the channel. Channel exists between source and drain, right? So this is an extra region introduced in this FET called MOSFET, right? So this is a structure, how it looked like. This B terminal, don't worry, for your level that discussion is not required. This is body is discussed while fabricating the device itself. Our higher semester students, when they study VLSI subject, they discuss this. Okay, but for connectivity and symbolic representation, these three terminals, gate, source and drain, are important, and if you know that, that is more than enough. So again, three terminal device, but fourth terminal is a body here, right? On the body, or this is a base on which the device structure is built. That is the idea. Okay, this acts as a support for this entire structure. So that is a base, foundation, you can say, or body of the device, you can say, right? So till now, till today, many ICs that we see in most of our computer chips, or maybe in mobiles or memory devices, right? There are you have calculator everywhere. You will find these MOSFET devices as a building component in most of the ICs. So that is a practicality, the application of this MOSFET. MOSFET is there in all these ICs, from beginning, from small application to larger application ICs you will find, but the only number will change. In the beginning, maybe 30-40 years back, the ICs what were available were having around 10,000 transistor on each chip. Now today you find millions of transistor on this kind of chips, and till sophisticated ICs you have today, where you will find billions, not millions, billions of MOSFETs on it. So these IC technology is because of this MOSFET till today. Today people call it as a FinFET. Today's Intel and other companies which are manufacturing ICs, they use FinFET. Same MOS they replace with Fin, Fin. Fin is a structure, how it looks like fin of the fish. So the device structure looks like that. So naming is it is renamed like FinFET. Okay, but today's scenario is that. But before that, you had the MOSFET in every ICs. So yeah. So coming to next slide, operation. Before going to operation, let me discuss the classification of this MOSFET. Just a second. Yes. Classification. Yesterday I was talking enhancement mode MOSFET and depletion type MOSFET. So MOSFET only we are discussing, but there are two types. This enhancement type MOSFET is used widely, so we should understand the working of this enhancement mode MOSFET. And then again, depletion type, it has got different application. Okay, but less compared to enhancement. Enhancement type MOSFET is used most widely. So the simple structure when you write MOSFET, it looks like this. So I'm starting with enhancement. So enhancement MOSFET will not have any channel developed between the source and drain. I said already three terminals: source, drain, and gate. So only concentrate source, drain terminal, gate terminal. But there should be a path for the current flow that you have to establish. Channel we call, right? In MOSFET, we call a channel, or even in FET, we call it as a channel that should exist between source and drain so that current can flow easily. So that uh, yes, channel you have to establish. So how to establish that channel? First, yes, uh, you have to apply the positive voltage between the gate and the source. Here, with the polarity plus connected to gate and negative connected to source, that will help you in building or establishing channel between source and drain. That I will show in the next slide. But this MOSFET is basically off-state device. Offstate in the sense, it is not able to conduct when you are trying to turn on. Only when your gate source voltage exceeds the threshold of the device, it starts conducting. That's why we call, even if you check with the VGS is equal to negative voltage or zero voltage, it won't conduct. But FET was conducting. But in enhancement MOSFET, it is not possible. Your device won't conduct. Why? Because there is no channel established in the fabrication. It is a channel is not available, right? Channel is not present. So that is what even in BZT we say the transistor minimum takes 0.7 volts for turning on, right? Silicon make devices. Even diode, 0.7 is the cut-in voltage of the device, we say. So once your input voltage applied exceeds threshold voltage, then you can say that device starts conducting, right? So similarly, in this device also, there is a threshold voltage above which it starts conducting. Means your gate source voltage applied should exceed the voltage, that is threshold voltage, then it starts conducting. Let us see next slide, you will get more clarity. Same structure I have written, but I have added the batteries just to see the operation, how it behaves, right? So I have connected gate source voltage, what I was talking, very important point. Gate source voltage will control the flow of current through the device. Even in FET, I discussed the same. If you have gone through PPT slides, what I have shared in the YouTube channel, you please go through that. Then MOSFET will be easy. Those who are not following, those who are not going through FET, PPT, available in Google class also, and and it is explained by me in YouTube channel. Please go through. I have shared the link, and you understand FET first and then come back to this MOSFET. So in enhancement MOSFET, this is a terminal of a battery I have connected just to demonstrate the working of this or explain the working of this device. So VGS is this. So what is the polarity of a battery you have connected? Positive terminal connected to the gate. This is my gate, yellow line, colored layer, gate. And this is silicon dioxide insulator, what I was talking, MOS. What is that? Metal oxide semiconductor. That is nothing but insulator. And this layer, white layer, is insulator. That was not there in the FET. and that is present here, right? So just below the SiO2 layer or insulator, you have to establish a channel. Here channel is established because you have connected a battery with this polarity. So what happens, how it is possible to establish this channel? Let us check. This positive terminal connected to gate will attract, right? It will attract electrons from where? From the substrate. What is the type of substrate I am using? I am using P-type substrate. Substrate is nothing but a body of the device, I said, right? So this substrate region is positively charged carrier region. So meaning is holes are the majority carriers, but electrons are minority carriers. And those minority carriers in P-type substrate get attracted by the positive terminal of a gate voltage, and these electron negative charges, minority carriers, get attracted and they start coming towards the this layer or very close to this insulator. They accumulate here. So this is a place they have accumulated the electronically, that is electrons have accumulated here, establishing negatively charged region called inversion region or inversion layer. Yes, yeah, I'm sorry. This, just see, there is a layer between source and drain. We have established a channel. How this negatively charged channel is established? Because you have applied the voltage accordingly and you are attracting the minority carriers from uh, P region, and negatively charged electrons, minority carriers, are coming and occupying the space here. They cannot enter into this region because this is an insulator, right? Insulator, they cannot enter, so they accumulate here. So this insulator end uh, layers, if you observe, they act as two plates of capacitor, right? Capacitor has got dielectric constant, right? Similarly, this SiO2, silicon dioxide or insulator layer also has got dielectric constant, right? So here, um, positively charged carriers will attract electrons, and this is how channel is built. Now, once channel is built, even with the small increase in the voltage here, you can observe large current flow through this channel from source to drain. So that is how this device works. This VDS definitely to forward bias drain source voltage, you have applied some voltage and just you are controlling the operation fully with this VGS, gate source voltage, right? That is what I explained here. Inversion layer, you should be able to tell what is inversion layer. Why it is enhancement type MOSFET, I said, because you are establishing channel, and channel was absent in the beginning. That's why you are inducing a channel or establishing a channel. That's why this MOSFET is called enhancement type MOSFET. Yes. So if you know the operation, now we discussed the operation here, how to establish and see the conduction. Now the same operation, we can plot the graph, right? So this is a transfer characteristics graph. You can see previous FET transfer characteristics graph also we have seen. Now also you can see, you can note down the difference, right? X-axis I have gate source voltage and Y-axis I have drain current. and this is the drain characteristics I have plotted. So let us check what is happening. So when VGS is 0, current is also 0. When VGS is increasing, yes, after some value of VGS, your device starts conducting here. So what is that? Threshold voltage, what I discussed in the beginning. Threshold voltage is a minimum voltage required for the device to turn on, right? So at this point, approximately 1 volt or 1.1 volt, my MOSFET is conducting. Enhancement type MOSFET is conducting, right? So after that, with the small variation in the gate source voltage, you can see the variation in the current, the increase in the current, right? So this is how your MOSFET is behaving for change in the gate source voltage. That's why it is called, yes, voltage control device. This gate source voltage is controlling the device operation or conduction of current in the device, right? Coming to drain characteristics, you see drain characteristics or output characteristics are nothing but it is a graph between output voltage VDS versus ID. So at different values of VGSs, gate source voltages, I am varying VDS on the x-axis. I am noting current values and plotting the graph. So at one value of VGS, suppose say 1 volt at threshold voltage, your device started conducting and you can see the current. In the beginning, there is a variation in the current. After that, it remains constant. So there is no effect of VDS after some point, right? VDS you are increasing on x-axis, but current is remaining constant. So what it means? Only for VGS means VGS has more control over VDS. Here also you can see ID current increases up to this point. After that it is constant. Means VDS variation has it doesn't have much control over the device. Only VGS 2 volts instead of 1 volt, you have given 2 volts. So magnitude of the current is increased to this, right? Magnitude of current is increased here for VGS is equal to 3 volts, approximately 4 point or 5 milliamps. This is 8 milliamps. You can see current at VGS is equal to plus 4 volts. Like that, if you keep VGS is equal to 5 volts or 6 volts, your current, you will get somewhere curve like this. So that is how current magnitude is decided by the gate source voltage. And in the beginning, this variation in the current, what you are observing, this region we call it as a ohmic region. Already we have discussed. After that, the current is almost remaining constant. This region we call it as a saturation region, right? Where the current is almost constant with irrespective of change in the drain source voltage. That is drain characteristics. This is how your MOSFET characteristics are characterized. So uh, yeah, next, once you know the operation of enhancement type MOSFET, you can go to depletion type MOSFET. Enhancement, what we did, your MOSFET started conducting at after threshold voltage, after VGS reaching a threshold voltage. At VGS is equal to 0, your current is 0. You can observe in the graph very clearly. So it is normally off-state device we call. Enhancement type MOSFET is off-state device we call. Why? Because in the beginning, channel is absent, no current flows through the device. So it is your job to apply the voltage and turn it on, right? So now coming to depletion type MOSFET, this is how the structure I have taken. Same MOSFET only I'm talking, but why you call it is depleted MOSFET. Enhancement MOSFET, you enhanced the channel, but here depletion type MOSFET, you have channel already present in the device structure itself. So just try to understand the terminals. Source again, the blue colored one, this region is source region, this region is drain region, and this layer, what is shown white colored layer, this is a channel. Negatively charged charge carriers are accumulated here. They have occupied the space, and no, it is established in the fabrication itself. You need not do any thing here to establish a channel present. So even with small voltage or even 0 volts at the gate can turn on this device. So that is a change from the enhancement type MOSFET, right? So depletion type MOSFET, channel exists. That is taken care, right? So as you know, again, I need not repeat, but no, if you have till doubt, some people have doubt, I can tell again that this region is source region, which is very heavily doped with the N types material, and this is a drain which is heavily doped with N type material. That is N plus indicates it is externally doped, right? Highly doped region. Okay, so N type channel you are establishing because you are talking about N channel MOSFET only, but depletion, because depletion there is a channel exist. That is what the thing. This black colored layer, what is shown here, that itself is a oxide layer or insulated layer, what I discussed in the previous case, right? Silicon dioxide insulating layer we call, right? So this is gate. Your gate is sitting here, where you have to apply the voltage and see the conduction in the device, right? Yes. So therefore, when gate source voltage is 0, current can flow. One second. Yes. Chetan. Yes, Chetan. Yes. Yes, fine. So therefore, when gate source voltage is 0, current can flow because channel exists. That is a reason. You need not establish